forgot to turn on the recording. So we'll start the recording now. Oops, sorry. So we've got these three resonance structures. This one, though a minor contributor, decreases the amount of positive charge on the carbonyl carbon. That's the resonance structure that can happen in a regular carbonyl group, because in a regular carbonyl group, this other thing that's attached is either hydrogen or carbon. It doesn't have any lone pairs, so you only get the two resonance structures. This third resonance structure is what causes a lot of the acid derivatives to be less reactive towards hydride reduction, for example, than the aldehydes and the ketones. Aldehydes and ketones have these two resonance structures, but not this one. The more this is contributing, the less reactive the carbonyl derivative. Which should make sense, right? Because the less partial positive charge there is on the carbonyl carbon, the less it's going to attract the nuclear bond. And that's kind of related to electronegativity as well, because you'll notice that in that third minor resonance contributor, there's a positive charge, formal charge, on the heteroatom. The more electronegative the element, the less it's really going to want to have that partial positive charge. But that's not the whole story. The piece of the story that's missing that enables us to explain within the halogen series why the acid bromide is more reactive than the acid chloride. And the acid chloride is actually more reactive than the acid fluoride. Right? Even though fluorine is the most electronegative element of these three, the order of reactivity goes like this because this is a bigger resonance contributor than this. And that's a better resonance contributor. So if you're looking at the amount of contribution, these arrows go like that. This one makes a bigger contribution. This one makes a smaller contribution. And the smaller the contribution made by this minor resonance structure with the pi bond to the leaving group, the more reactive. So the question is why, even though fluorine is the most electronegative element on the table, why does this pi bond to the fluorine make a larger contribution than the pi bond to the chlorine and the pi bond to the bromine? And the answer is to be found in molecular orbital theory. And it's because orbitals interact best with other orbitals of the similar size. This is a 2p orbital on carbon interacting with a 2p orbital on fluorine. They're very similar size, so when you bring them together, you're going to get lots of good overlap. pair of identical or almost identically sized 2p orbitals. This is a 2p orbital on carbon overlapping with a 3p orbital on chlorine. Well, most of that 3p orbital is up here and here, which is not where the 2p orbital is. So when you try to get those two orbitals overlapping, the 2p orbital is kind of in here. Well, you've got kind of crap overlap, right? There's not much overlap because the 3p orbital extends too far out. And so we get poor overlap. And for the bromine, we're talking about a 2p orbital overlapping with the 4p orbital. That's going to be terrible overlap. Almost all the electron density of the 4p orbital is out here, where the 2p orbital can't even touch it. Right? So I'm going to say no overlap. It's not really no overlap, but it's really minimal overlap. So because of the mismatch in orbital sizes between the 2p orbital on carbon and the 4p orbital on bromine, this makes really small amount of contribution to the resonance hydrogen, which means it's not able to stabilize that partial positive charge, which makes this one all the more important, especially when you consider that those electronegative elements are pulling electron density away as well. So you're inductively pulling electron density away. That's destabilizing that carbon. But in the case of fluorine, you've got this resonance effect that counteracts your electronegativity. So inductively, in the sigma bond, you're pulling electron density away, but then you're donating some of it back through a resonance effect. Chlorine's not very good at donating back through the resonance effect. Bromine is really crap at donating back through a resonance effect. So oxygen and nitrogen, in the case of the anhydrides and the esters and the amides, are all 2p overlap. So when you consider the contribution from the amide, and I'm going to use DMF as my example here. Back up to the amide. We've got this resonance structure. We've got this resonance structure. The minor resonance form, this makes such an important contribution. And in the proton NMR, those two methyl groups actually show up as different chemical shifts. You don't have free rotation about this bond because the pi bond can't rotate, right? You can't rotate around a pi bond without breaking it. If this were just a sigma bond, you'd have free rotation, the two methyl groups would interconvert, and you would expect to see them at the same chemical shift. But it doesn't do that because this resonance structure is an important enough contributor that it stops that rotation around that carbon-nitrogen bond, and you can have different chemical shifts. And the other thing is, in the IR, you see a reduced wave number, 1650 to 1680 for the amide carbon-oxygen double bond stretch, whereas the ester carbon-oxygen double bond stretch is about 1735, 1750. The carbonyl group of the aldehyde and the ketone is about 1710, 1720. So this is a weaker bond. Why is it a weaker bond? Because in that resonance structure, it's only a single bond. So you are increasing the strength of the carbon-nitrogen bond because of this resonance contributor, which is causing you also to lose free rotation, and you're decreasing the strength of the carbon-oxygen bond. All of that evidence from the NMR and from the IR goes along with our thought that this is a much more important resonance contributor for nitrogen. Why? Well, nitrogen is not as electronegative as the other elements, which means it's better able to stabilize this partial positive charge. It's got the same size orbital as carbon. Carbon and nitrogen are closer in size than carbon and oxygen because they're right next to each other on the periodic table, much closer in size than carbon and chlorine or carbon and bromine. closer in size than carbon and fluorine. So we've got the best orbital overlap from the size perspective, the best ability to stabilize that partial positive charge from electronegativity perspective, and the least polar sigma bond, because nitrogen is a lower electronegativity than carbon. Not quite the least polar. Nitrogen is actually more electronegative than bromine, but we've already talked about how bromine has crap overlap, so this is basically a non-contributor. So you can think about other acid derivatives that I haven't seen before, like thioesters or acyl cyanides, and you can think about, all right, how good is this contributor going to be? How good is that resonance contributor? More important than the inductive effect. The inductive effect, which is the second factor, really doesn't explain the reactivity very well at all. It's mostly this pi orbital overlap that affects step 1, and the ability of the leading group to lead that affects step 2. Fortunately, those trends reinforce each other. Right? The better leading group, right? Bromine is the best leading group because HBr is the strongest of those acids. The better leading group and the least ability to do this pi orbital overlap, they go together. What about the anhydride? Why is the anhydride so much less reactive than the ester? They're both oxygen. One of them's a terrible leading group, the other one's a good leading group because of the resonance stabilization, so that certainly affects it. But what about the relative importance of the minor resonance structure of the anhydride versus the ester? All right, so we can write this minor resonance structure. Good orbital overlap because oxygen and carbon are both the same size, but less good than for the nitrogen because nitrogen is less electronegative. And then we can draw the corresponding resonance structure. This is a whole lot more reactive than that one. Even though that's a carbon-oxygen pi bond, and that's a carbon-oxygen pi bond. So what the hell? Why are they not identical in reactivity? Right, we've got a stabilized partial positive on this carbon, we've got a stabilized partial positive on this carbon. What's going on?
Does it have to do with the other carbon in the anhydride?
It has to do with this carbon.
Right.
That carbon is stabilized. This carbon hates this. This carbon really doesn't like that structure because there was a minor resonance structure for that carbon. It's going to look like that. So this carbon is going to look at this oxygen and say, dude, you're supposed to be forming a pi bond with me and stabilizing me. And this oxygen is stabilizing the other carbonyl instead. So this carbon is saying oxygen, hey, dude, now you have a positive charge, you asshole. You're supposed to be stabilizing. So this one is less stabilized. It's actually destabilized. And this oxygen can't stabilize both of the carbonyls that it's adjacent to at the same time. Right? So this actually becomes more reactive. This oxygen doesn't have that split loyalties, right? There's only one carbonyl it's next to. It's only got one carbonyl it's trying to keep happy by stabilizing it. It doesn't have that kind of pull towards both. So this is a very bad resonance structure because it's got positive charges, formal charges on adjacent atoms. And you can't stop that, right? If this oxygen formed a pi bond to that carbon, then it wouldn't be stabilizing this one. And if it tries to form a pi bond to both carbons at the same time, then you'd have a 2+ charge on oxygen, and oxygen won't be crashed. Right? It's got to choose. So even though the orbital overlap is the same, when you're destabilizing the other side of the end contact. So I'm not going to ask you to go through and order the carbonyl, the carboxyl derivatives in order of reactivity and then explain the 3 factors on the quiz, because it's going to be a reaction quiz next Tuesday. But I'm going to ask you on the exam to rank a set of carboxyl derivatives in order of reactivity and then use the 3 factors to explain the order that you read. That's definitely going to be a question on the exam. You can count on it, so you can be ready for it when it comes. All right, let's stop this recording.